Hey everyone, we're going to get started now. So thanks for coming to another session of Applied Learning Group. Today we have Connor DiPaolo, who is an intern for the summer here. He worked on the spam team, and he's starting his sophomore year at Harvey Mudd in a few weeks. So today he'll be talking about optimization, and yeah, welcome.
Yeah, okay, cool. So can I get like an overview? So how many of you have taken, I'm assuming like a linear algebra course? Yes. Multivariable calculus? A little less, yes. How many of you know what the derivative of like x transpose ax is with respect to x? 5? Okay, we're gonna be comfortable with that now. So like I pretend, when you see like x transpose ax, pretend it's ax squared in like a single variable case, and everything's pretty much the same. There's gonna be a lot of that. So if you guys think that there's too much linear algebra, let me know, and I can like convert them to single variable cases. But yeah, so I'll try to bring that back continuously. So convex optimization So convex optimization is a field about how to solve large optimization problems, which we'll see defined here. So you might have used machine learning in some of your teams. I know some people here definitely have. Also, signal processing engineering uses this a lot. When I took this as a course, it was in the engineering department at my school. So this is used a ton in tons of different fields. Operations research, for example, is a lot of this. Yeah, pretty much. And so with that, it can be very, very applied or very theoretical. Note that I sort of swayed it towards the applied side, and this is like more of an applied topic, but like I saw some professor in my school that does like analysis work has a paper he published like a couple years ago on like something in the simplex, and this is some complex optimization type topic that he was doing in like analysis. So things can sway both ways. We're gonna see more applied stuff. So as Jason Fennell was hinting at during the EPS, there's way too much to cover if I was gonna try to cover a lot of stuff. So I'm not gonna cover duality. I'm not gonna cover more than 2 algorithms, but I want to keep it applied for you guys. So we're probably going to we're going to cover like set convexity, function convexity, optimization problems, convex optimization problems, and then talk about algorithms, aka gradient descent and Newton's method, and why Newton's method is better than gradient descent. Yeah, pretty much. And then so, as I say on here, and you might have seen the email sent out earlier today, I sent out these slides, the notes that I derived these slides from that have duality in them, if you want to look into more of that. And those are shorter. They're like 20 pages or something. So it's not short, but it's like shorter. And then this book right here is the canonical standard if you're going to look into any of this. It's free online as a PDF. And also Boyd has his lecture videos from Stanford online as well. So if you want anything more at all about this topic, that is the right reference to have. So a set, pretend this is like a set of numbers in R2 or the plane. So I just draw a little box and these are the numbers. A set is convex if you can take any 2 points in the set and draw a line between them, and all those points in that line segment are in the set. So this set is not convex because if I take these 2 points, draw a line in between them, these points are not in the set. So sort of defining that, it's pretty much what I just said. And so we sort of need to have like a mathematical definition. We need to define what a line segment is, or they would call it a convex combination. So if you have an affine space or linear space, there's a subset of that, and you have some parameter theta, which is somewhere between 0 and 1, and you say theta of x plus 1 minus theta of y. So you could think of that as a weighted average between the 2 points. And at one extreme, if you have theta equals 1, it's only x, which is this case. And if you have another extreme where theta equals 0, it's only y. And so by varying that parameter, you sort of span the 2 points in between them. So that's a convex combination, or just think of it as a line segment between 2 points, x and y. And so the mathematical definition of what a set is, or of a set being convex, is that for every x and y in this set C, the convex combination for any theta parameter between those x and y is still in C. So that's just the same thing we saw in the diagram. You draw a line segment between x and y, and that is still in the set. So there's a lot of interesting sets that are convex. One of my favorites is the space of continuous probability distributions over Rn. So this is like a pretty complicated set. You have every point in this set defines a valid probability measure, so p of x, such that it integrates to 1 over all of Rn. And that includes things that are on compact domains, or I forgot the spaces. And so all of the probability distributions over Rn that are continuous is convex. And so we can prove that because the only two properties that we're caring about right now are that you have some p of x function that integrates to 1 and is positive, and two functions f and h that we're trying to take a convex combination of, and we're trying to prove that they're still in that set if we take any convex combination. And so you have some parameter theta again, and we know that because both of these are positive, any convex combination is still positive. And then because the integration is linear, we can just expand out into the sum and break out the theta. And it's theta plus 1 minus theta because these two integrals are 1 by definition because they're from the set. And so that equals 1. And so the convex combination integrates to 1 and is positive, so the set is convex. And that's usually how you'll prove pretty much all sets are convex. It's pretty simple. So now that we know what a set being convex is, the more important definition we need is how do you know what a function is convex? So again, if you have a picture, convex functions are like bowls in some huge space potentially, but they look like bowls. And then concave functions are when the negative of the function is convex. So if you have the bowl and you flip it over, that is convex or concave. And then you could have functions that are neither if they just sort of like loop around. And then so sort of defining that mathematically, we have, actually it might be better to, so if you take any point, or effectively if you'd have any point on the function and another point on the function, if you draw the line segment between those and it's always, that line segment is over the function itself, that for any x and y, that function is convex. And so you take any input theta x plus 1 minus theta y, that 1 minus theta y, that line segment, input in the function, that is always less than the convex combination of the function values for that same theta. And so in the actual definition, that's what we have. So you input this line segment into the function, and that's always less than the line segment between the function values for a given theta. And then so it's generally speaking pretty terrible to prove that a function is convex with this definition. So there is things called first order conditions, and I'm going to skip to the more important second order conditions. So how many of you know what a Hessian is? Second derivative. So a Hessian, pretend this is the second derivative of f. It's equivalent in the single variable case. And so this is just a matrix that is like the second derivative. And so how many of you know what a positive semi-definite matrix is? Yes, yes, yes? Okay. So if you think of this as the second derivative, pretend it's positive or non-negative in the semi-definite case. So a function is convex if and only if it's twice differentiable, if and only if its Hessian is positive semi-definite. So that means that the second derivative is positive or non-negative. And you can think of that as being like the first derivative is always increasing, so it's going to be bowl-shaped effectively. You're sort of asserting that. Examples of this, so the log is concave, so the second derivative of log is negative 1 over x squared, and so ignoring 0, that's always negative, so f is strictly concave because it's negative and not non-positive. And then the e to the x, x, is the second derivative is e to the x again, and so that's positive strictly, and so it's strictly convex. In the multivariable case, so if we have e to the x transpose x, which is just the sum of the different dimensions squared, every element of the Hessian, so we take two derivatives, and you get 4 times xi, xj, and then times the function. And then if you can intuit, if you're familiar with this, that is 4 x transpose, the outer product, times e to the x transpose x. And if you know the definition of positive semi-definite in terms of Z transpose A, Z as being positive or non-negative. That's equivalent to the eigenvalue definition that you may have seen. It's pretty easy to see that if you group the scalars out, you can just see that this is 4 times a squared quantity times this non-negative exponent, so it's non-negative. And another example, quadratic functions are convex if and only if they're like the bilinear form inducing matrix is positive semi-definite. So if you take 2 derivatives, it's 2a. So those of you, again, no matrix calculus, pretend this is ax squared plus bx plus c, and everything's like just a number. And if you take 2 derivatives of ax squared, you're going to get 2a. And so that's the same as this. And so that's positive if a is positive, or non-negative if a is non-negative. And so that's the same as this. Another example, so if we have we have an affine combination, so if you insert ax plus b into a function and treat that as a new function, that won't change your convexity of the function. And so that's going to be convenient later, as we'll see. But basically, if you take 2 derivatives, it just brings out an A transpose and an A on both sides of the old derivative, or second derivative. And then you can do the same grouping trick to have this. It's effectively asserting that the old function is convex. If you look at the definition of positive semi-definite, this will map somewhere to some vector, but that's fine. Yeah, pretty much. If you need any more help, let me know with the linear algebra. So yeah, I guess we can probably slow down now. So this is the important stuff. Convex optimization problems are defined differently than optimization problems, but in general, you have some function that is like outputs a scalar, and you have some input that you're trying to minimize or maximize, and you have some constraints on what values you say are okay. So I'm assuming a decent amount of you have seen like linear programming maybe before. So that is an optimization problem that is seen a lot in operations research that I'll touch on a little bit. And that's like a whole field is just like converting things into linear programs and solving them. So that's pretty important. And there are a bunch of other problems. If you've seen like support vector machines, if you've done like machine learning stuff, that is a quadratic program. There are like semi-definite cone programs these are like generic classes of programs. But in general, an optimization problem is just you have some function that you're trying to optimize and you're trying to find the value that optimizes it. So putting that into math, you have some problem statement that says, I want to minimize this objective function that takes in some quantity. It might be a vector, it might be a scalar. And then I have some restrictions on where that function is going to lie. So it says 0 here, but that doesn't necessarily mean 0. You could have like x squared is less than 6. You would just move the 6 over, and that's equivalent to this. So you have inequality constraints. You could say that you're bounding where x can be in your objective, or you can have equality constraints. So you're saying that x has to equal 6, minimize x squared, it's going to be 6 squared because you have to be there. But if you're in like a larger vector space, you can have more leeway with that, where x can actually be. So the actual domain of your problem, you're restricting yourself to these constraints and the domains of the actual functions in here. So if this is like log x, you're asserting that it's also positive implicitly. Yeah, that's more of a technicality, I guess. But yeah, in general, you can have countably infinitely many constraints if you want. So a convex optimization problem is the same as an optimization problem, but we place restrictions on what your constraints can be and what your function can look like. So a canonical example might be I am trying to minimize how far away I am from the origin and bounding myself in between some box or something. So I'm saying I must be like greater than 5 away from the origin, minimize how far away from the origin, it's 5. And so like intuitively, a convex optimization problem is minimizing a convex function or maximizing a concave function, because that's equivalent. Minimizing a convex function on a concave set for your domain. So you can think of that as like having some quadratic coming out and then drawing a little circle around, and that's where you can lie in the quadratic. That's a convex set, and you're minimizing this value of this function over that convex set. And so equality constraints are convex, but you can't have linear equality constraints are convex. So you can't have like x squared equals 6, although you might be able to like do some deduction and say like x has to be one of these two values. But you need to have a linear equality constraint to be in like a canonical form for your problem to be convex. And then if you have an inequality constraint, it has to be a convex function is less than 0, because you might think about that as saying that like x squared minus 6 is less than 0. That domain right there is convex. So if you have like, let's say negative x squared plus 6 is less than 0. So that's like if I drew a line out and then had this quadratic over here, you're going to end up having part of your valid set is over here and part of the valid set's over here, and that's non-convex because we can have some point in between if we take a convex combination. So that's how you're restricting your domain so that your problem is like easy to solve algorithmically, you might say. There are a lot of benefits to having convex optimization problems. The primary benefit for you guys would be that you can solve them in like generally polynomial time, like with algorithms that are very efficient. The real like intrinsic value is that if you have some solution to your problem locally, so you might have on that other problem where it's like half of your problems over here and half of your problems over here, you can minimize something here or over there. But if you have a solution on a convex problem in some location of your space that's like locally the best, it's globally the best as well. And so that induces a lot of help when you're like trying to generate algorithms for these types of problems. And so I think I might, should I do the proof? Yay or nay? Hands up if I shouldn't do the proof. Got one yes. So, okay, I won't do it. You can look at the slides if you want. It's just straight from Boyd as well. So this is just saying if you have the smallest value of your ejective function that's feasible and within some little ball in some space, that R is also infinity, basically. So you can expand that ball and it's also the best. So what I was talking about earlier, linear programs. So if you have a lot of graph problems like network flow, like max flow, min cut, if you've heard of that before, there are a lot of just like kind of algorithms that are very like on paper, just do this specific steps to solve all these problems. But in general, there are algorithms to solve the more general class of those types of problems, which are linear programs, where you're minimizing or maximizing, because linear functions are both concave and convex. So minimizing or maximizing some linear, some like inner product, such inside a polygon, also subject to equality constraints. And so you can also find out if you do some finagling that these two are equivalent, so you could drop this or drop that and it's fine. But basically you end up asserting that you're inside some polygon, or it might be called a polytope in a larger space, and you're saying find me the furthest away point in this polygon in some certain direction. So I'm like bounding myself in a house, and I want to say go north as far as I can, and that's what the problem is. And there are very efficient ways to solve that. The older algorithm is called the simplex algorithm, and you can solve these things with interior point methods faster using what we'll discuss later, which is Newton's method. And that's the faster way that I think MATLAB will do now. So quadratic programs is, so pretend that this says 1/2 p lowercase p x squared plus qx plus r. It's just some quadratic function. And then this is the same bound me in a polygon constraint, and this is the same equality constraint, which is almost equivalent. But I don't think you can drop them because you have the quadratic in there. And so the assertion is that P is positive semi-definite, so it's symmetric and positive semi-definite, which means that this function itself is convex. That's all you're asserting. Because before we proved that a quadratic function is convex if and only if this matrix right here is positive semi-definite, so that's all we're asserting, so that this is a valid convex problem. If you have a negative semi-definite like matrix right here, you can maximize it. That's fine as well. And so if you're familiar again with support vector machines, you can write your support vector machine problem in this form and solve it like that with a general quadratic program optimization solver. Yeah, pretty much. So, interesting problem, and this plot took way too long to make. You might be concerned with finding the center of a polygon, and that sounds like a terrible problem that people never use, but actually if you're solving linear programs using interior point methods, this is like the center of that actual algorithm. So we're trying to find a center of a polygon, like ax is less than or equal to b, and so we basically say that when you get close to the boundary of that polygon, so b minus ai transpose x, you're going to have this log barrier increase to infinity, the negative log barrier. So pretend that this is like 0 right here, and it's just log of x. If x gets close to 0, log is going to shoot up to infinity. And so that's what you're asserting. And so you can see the sort of the contours of one of these problems for some a and some b here. And then this is the progression of one of these algorithms. This is gradient descent right here to solve this problem. And so if you use, this took like 100 iterations. If you use Newton's method, it'll take 11. So yeah, pretty much. And when you're using an interior point method to solve a lot of optimization problems, so you would have some like affine type constraint like this, and you're basically, or you would have some log barrier for your problem, and then you would start off by solving this problem with this analytic centering. So you're saying, find me the center of these constraints. And then so you have like a first solution there, and then you start weighting more your actual objective function until this objective becomes negligible. Although you still maintain these infinite constraints right here because the infinity will shoot up higher than whatever the objective is. So you end up just sort of reweighting your problem until you get to the actual optimum, starting at this center of the polygon, or some shape in whatever dimension you have. Another example that you probably all used, I'm assuming, even in like high school, is fitting a line to data. So least squares linear regression. So if you have some, and you can represent that as how I'm about to describe it, but you have some tall A system, so it's overdetermined ax equals b, that you can't solve with like in A or x equals A inverse b, because A is definitely not invertible if this is like super skinny matrix. And so one way to do that was say we want to find the solution that is closest to b itself. So ax minus b is the smallest. And we would just say ax minus b L2 norm, and that should be squared. And then you can expand that out to this quadratic form. And then this, if you're familiar, is always positive semi-definite. You can prove that. And so if you add optimality for unconstrained problems, you just take the gradient of your function and set it equal to 0, and you can solve that if there's an analytic solution. So we just say the gradient of f, which is this thing, pretend this is a squared x squared, and so that would just be 2a squared x, and then pretend this is negative 2ab, I think, yeah. So, and then you would just drop the x when you, or negative 2xab, so you would just drop the x when you take the derivative. And then you can drop those 2's, move this over, and find your solution, which is A transpose A and inverse A transpose B. And so if your A was actually invertible, you could effectively cancel and get A inverse B back. And so that's the closed form solution for least squares that you probably maybe have seen before. And this is the thing that your computer will do if you try to fit a line to data usually. This is, yeah, effectively. And then if you're more familiar with machine learning problems, logistic regression is we have some data set with some xi's and yi's from 1 to m points. And then every y is either a 0 or a 1. And we're trying to predict a probability that y is 1, which is equivalent to the expected like y hat, almost the approximate value of y we're estimating. And so we just squash this linear transform of x into some function that will map that into 0 and 1 for us. Call that the estimated probability. And then we're trying to maximize the probability of our data given our parameter vector, assuming you're not doing any Bayesian stuff. So that's equivalent to maximizing the log of the probability of your data given the parameter, because log is monotonically increasing. So if we maximize some function x and we map that into x squared, or sorry, log x, it's going to be the same. Or the maximum value is going to be the same, although the objective value evaluated at that point obviously is not. So you can expand that out, and you end up having this. It's a sum of all of these individual components. Like you might call that the loss at each point, because each of these only involves one of the points. And then that's just this function value right here. And so if we want to show this as convex, because it's unconstrained, all we have to do is show that this, because we're saying maximize, all we have to do is show that this is concave, or the negative of this is convex. So if we look at the gradient of, it looks like a lot of math, so I probably won't. So if you look at this line right here, you can deduce that the gradient of each loss is just the value minus the predicted value times x itself. And so if we take another derivative to get the Hessian for each loss, we would have negative of the sigmoid, or the function we're squashing into, of the linear combination times 1 minus that times this outer product. And as before, if you use the definition of positive semi-definite or negative semi-definite, we would just multiply by z transpose on both sides, and then, or z transpose and then z on both sides, and then group these outer products together. And that would turn into something squared, so that wouldn't change the sign. And so this is always positive, this is a negative sign, so it's always negative or non-positive. And so that's how we know it's a convex problem. Did I just lose everybody? No? We're good? Are we good? Yeah? Okay. So a lot of you are probably concerned with like the algorithms of how to solve these problems, and I think they're pretty interesting. How many of you have heard of gradient descent? Yes? A lot of people. Okay, cool. So you might have heard that in the context of like deep learning or something, or maybe in the context of just general solving like a machine learning problem, probably. Effectively, we're trying to solve some optimization problem, and I'm going to pretend it's unconstrained here because I didn't talk about duality and stuff. So we're trying to solve some optimization problem that's unconstrained. It's just minimize this function, and then we can be anywhere. So this optimality, this solution, is when the gradient is equal to 0. And in the case of least squares, we were able to solve that in closed form, like we just A transpose A inverse A transpose B. But in general, like with logistic regression, we weren't able to do that. Like you generally have intractable problems if you're trying to solve for the gradient exactly. And so that's where these numerical methods come in to give you a good solution whenever you want them. So this pot looks very nice, if I do say so. The dumb algorithm, which is actually like the centerpiece of all deep learning that people will do, is you have some function, so pretend this is like a quadratic coming out almost. And we start somewhere, and so this is like some big surface in like a bowl that I'm sort of standing in. And I'm standing somewhere on the bowl, and then I see like closest to me where the direction of down is, and then just take a small step in that direction. And then I'll do that a bunch of times. And then eventually, you can say that I'm in the bottom if I do that enough, and you can prove that. But the problem and that's called gradient descent, because you basically find this gradient that's saying where your function is going up and then walk backwards. And you can find the gradient usually in most problems you're going to deal with. So the problem with that is, that is not a problem in general. It's not a problem in this case where your problem sort of looks the same everywhere. So you might say that the Hessian is like some multiple of A identity, for example. Your problem will be, like the curvature itself is like uniform. But if you have a problem that's sort of squashed down, so this ellipse right here that's very like tight, and you could imagine even stretching this out a very long distance, if we pick a point out here, this gradient is going to be pointing like very far up. And then if we take a small step, unless we tune it exactly, we're going to be jumping across the side of the valley, or even jumping further out of the alley if we take it too far of a step. So in general, it's very hard to tune that step size exactly, because we sort of just preset the step size or have that sort of change automatically, but we don't have a general formula for the best step size in this algorithm. So it's just going to sort of jump across the valley and then as you progress, it's going to go like this and just sort of jitter around until you get to the center. But it's going to take way longer numerically than it would if you use a different algorithm that can account for that curvature, which is Newton's method. So yeah, pretty much. Even despite that, it's still used in almost literally all deep learning research. So that doesn't mean that this is never used by any means. If you have huge problems and you can't compute the Hessian of a problem, like in your computer, like you can't fit in memory, this is definitely the best solution for you, likely. Or some, not this raw I'm about to show you, but some variant of that is probably the best solution. So it's pretty simple. Basically what I just described is you have some function, some gradient, some step size at some time t, and this could be constant if you want. And then you have a starting point where you start on that bowl, and then the tolerance you want. And so if you shoot that to 0, it's going to be very accurate eventually. And so you start at 0, and then until the norm of your gradient is less than some epsilon. So initially your gradient is going to be pointing super far out because your function is like curving a lot. But eventually you want to find when the gradient is 0. So when that thing gets very small, then you could say you're done. And then at every step t, you will take your original value where you are currently, find the gradient at that value, and then take a step backwards, a small step, and then increase your time, and then return the optimal value at the end. And so that's a pretty simple algorithm, and it is. You can implement like a couple lines of Python easily. And this definitely works, and it's provable that you will get there on values of eta, I think. If the step size is too large, obviously, you're just going to sort of shoot out of the bowl because you aren't going in the right. You're going, like if I'm standing on this bowl right here, that Newton's method is scale invariant. So I'm using induction. I'm assuming most of you have seen that at some point in your life. I'm assuming we have the same starting point. So x of t is a of y of t, like for our inductive step, but also that x of 0 is a of y of 0. So that's all we're really assuming. And then this is the induction hypothesis. And then this is the actual optimal step we computed. And then we're assuming that g of y is f of a of y, which is we're going to call f of x. And so sort of like before, the gradient is a transpose of that. You can look in the matrix cookbook online, and it'll show you that. And then the Hessian is a transpose times the Hessian times a of the original function with our scaled version. And then trying to find the next iterate for y, we have initially, and we're assuming that the map is invertible, so A inverse exists. So we have y of t plus 1 is A inverse of x of t, because that's just y of t, right? And then minus the Hessian inverse times the gradient right here. And then if this is invertible, we can flip around the transpose and cancel those. And then we just have A inverse times the Hessian inverse times the gradient right here. And then this is just x of t again. Pull out the A inverse. So if we look at this solution right here, this is the same equation as right there. So we can just substitute x of t plus 1 in right here for the algorithm step. And then we have y of t plus 1 is A inverse of x of t plus 1. And then just move over the A and we have this. And so we can prove it by induction, and that's kind of fun. But yeah, so that's pretty much the whole talk. What the important takeaway is that you can solve problems if you express them in a nice form or approximate them in a good form in very efficient ways that are super accurate if you want to do these things like on a computer, for example. And problems are generally pretty easy to tell if they're convex or not. And so having that sort of tool in your toolbox when you're trying to approach problems like your work or whatever is generally helpful. And most of the tools you use today, like for example, especially machine learning, rely on a lot of these tools. Even if you're doing like more advanced stuff like deep learning, like it all sort of relies on this tool set, especially the gradient descent thing, ironically. It relies a lot on that. And there are a lot of approximations and heuristics that are used to make gradient descent perform better. But at the end of the day, you're just sort of performing some optimization problem, and that's how you like create these photo classifiers, et cetera. But yeah, any questions? Fastest one I've heard of, so I'm assuming it's the fastest one that everybody knows about. So I was telling this to Daniel, but if you watch Boyd's lectures online on Newton's method, for example, like he pretty much raves about Newton's method, and talks a lot of shit about gradient descent. So like it is a good algorithm in general for this problem. But that step, I think I should probably mention this. So this step right here is non-trivial in general. And especially non-trivial when you're dealing with a neural network that has like a billion, million something parameters. That's a problem. And what most people ignore when they just say, oh, there's a problem, I'm never going to use this algorithm, is that a lot of the times in your problem, like if you have some large graph or something, and that the degree of the graph is like at most 5 or something like that, like you can bound that, your Hessian is going to have really good structure that you can exploit in solving this system and do it really quickly. Like you might have arrow structure in your matrix. So if you have a matrix right here, and your matrix looks, your Hessian, this is your Hessian, looks sort of like a stripe down the middle and then like an arrow, you can solve that super fast. And or if you have like some like dense, some multiple of the identity matrix plus some low rank like outer product or something, like that can be solved super fast. And so it depends a lot on your problem structure. And so I wouldn't throw this away if you're approaching a new problem and saying gradient descent conversion pretty slowly. You should look at this even if your problem seems like it's pretty large. But in general, if you have less than like 5,000 variables, you could just use this straight up and use like a backslash solver on MATLAB or whatever, or like Julia, and that's fine. Yeah, does that answer your question? Okay. You had a question? No? Yeah?
If you know more than then can you
So I'm pretty sure that you couldn't solve it in closed form. The issue in general is that when you have the third derivative of some function that maps from Rn to R, that's going to turn into a tensor, and people hate dealing with those, and so most people won't do that analysis. Like if you look at the analysis for Newton's method's convergence proof, they'll say that the second derivative, the Hessian, is Lipschitz continuous, so that's just because they don't want to write down this tensor, basically. And so a lot of the analysis is sort of like restricted because people enjoy working with matrices more. But I don't know of any methods that use the third derivative explicitly, although it's like implicitly used for interior point methods, for example. Like you'll say your function is self-concordant, which means that if you restrict it to any line in your huge space or just have a scalar, that the third derivative is bounded, basically. And that's sort of similar to the Lipschitz continuous thing, but they'll use that instead because they don't want to deal with a tensor. Yeah, pretty much. Any more questions? Yeah, so you can usually, like if you're looking at deep learning package, all of them pretty much implement gradient descent. So some does not look like this. You're going to have like 3 more terms on here, probably like 2. And then this step right here is very heuristically optimized to some degree. There's this thing called the atom optimizer, which was published like about a year ago that you might have seen in the TensorFlow package. And so that within a couple months has become the de facto standard in that community for a lot of problems. And so that is a huge heuristically changed version of this. And there are a lot of those. Atagrad, RMS prop, I think, is another one. There are like probably 5 or 10 that are like commonly used, actually, like variants of this algorithm. If you're actually trying to solve just some generic convex optimization problem, there's this toolkit from Stephen Boyd, who wrote the textbook that is a lot of the stuff is based on, that I sent a link out to, called CVX opt. And there are versions, and that's in MATLAB. There are versions in like 3 or 4 other languages, Python, Julia included, where you can write down your problem in, you can like write down your problem pretty much like this in code, and it will give you the solution. And it'll like move your problem around in some interesting way, put it into a solver that exists on your computer. Then there are solvers for just generic convex optimization problems. Put it into a solver and then give you the optimal solution and say like, here's a bunch of statistics about how I got there. And that's in general what people will do if they're trying to just like experiment with like deriving new problems or creating some interesting problem. Like you can do like machine learning problems, just like write them in this form, solve them. And that's usually what you'll do if you're like experimenting again. But yeah, I mean, I've used Newton's method in gradient descent before for like machine learning purposes, but in general, not much other stuff because I don't do much other stuff. Yeah. Yeah, so there's a thing called Nesterov's conditions, I think is the name. You can look that up, but I'm pretty sure it's called Nesterov's conditions. And this, I've seen this in stochastic gradient descent, so let me talk a little about that. So when you deal with a neural network, usually what they use is not gradient descent, but stochastic gradient descent, because if you look at the Hessian, where was logistic regression? So this problem and a lot of problems in machine learning are the sum of some loss function for each example, including neural networks in general. And so what you can do is find the expected value of this and you can just throw in 1 over m in here to average it out, and that's fine. It doesn't change your problem at all. So what you can do is decrease this, like you can randomly select some examples, k of them, and say like some mini batch you might call it, and then find the approximate Hessian / gradient for those examples and then solve that. And that's called like mini batch gradient descent or stochastic gradient descent because you're finding the like expected value of this like stochastic version of your objective function. And so with that specifically, I've seen that you need the sum to be bounded, but the squared sum to be let me try to remember this. So the sum of your eta of t over all t, like to infinity, has to be, I think it might be, it has to be infinity, but your squared sum, so the sum of the squared terms, has to be finite. I'm pretty sure is the bound on that. But you can look that up. It's in also in Kevin Murphy's textbook for machine learning, so I know it's in there. But yeah, I can point you to that later as well. Questions? No? Okay, cool. Thank you guys.
Okay, thanks for coming, everyone. Next Applied Learning Group will be in 3 weeks.